What we're going to do in Chapter 6, or Chapter 16, is review scan projection radiography, briefly review CR, and then we're going to talk about indirect capture DR, indirect capture DR. Scan projection radiography is technology that was adopted from CT. And the original CTs were not a rotate translate, or it wasn't a technology that rotated around the patient, but it was rather a rotate translate technology, which is where the X-ray beam would scan across the patient and it would stop, and then you get some sort of rotation and reset, and it'd scan across another portion of the body and stop, and then it would kind of click again to a different section and scan again, stop. So the tube didn't rotate continuously like what we see in CT now. So the tube moved while the patient was stationary, and it utilized a fan-shaped beam that would just scan a portion of the patient's body at a time. And they moved that over to radiography and dedicated chest units. And how they worked in a dedicated chest unit is, let's say the screen represents the image receptor. We had a collimated beam that was just a fan-shaped beam that maybe it was the size of this much of the screen. So it was very closely collimated, and what it would do is there would be collimation, the X-ray beam followed by collimation, or X-ray tube followed by collimation, and then the patient, and then there was post-patient collimation, and then the image receptor. So the beam would scan across the patient from side to side or from top to bottom, and it would go across the patient, moving as the post-patient collimation and the image receptor moved along with it. So it was scan projection radiography. They were used on dedicated chest units. The difference really between CT and scan projection radiography is we were only interested in not cross-sectional anatomy in dedicated chest units, but rather in just chest x-rays. So the dedicated chest unit would be in a room with an x-ray tube and basically a wall buggy, and that's how we would shoot chest x-rays. I never worked with a scan projection radiography unit. In CT, of course, the patient's on a couch and the patient moves through the x-ray beam. So you had a thin collimated fan beam. The dose to the patient, because of the collimation, was lower than what it would have been with just a moving image receptor and an area beam, but it was still pretty high. So it was kind of high dose for chest radiography. Didn't last all that long. So where it was used in CT was primarily in chest x-rays. Now we still use it in CT and in bone densitometry. In CT, it's a totally different technology with slip ring technology, where the x-ray tube and the detectors rotate around the patient. And CT uses a much smaller x-ray beam now. But all that was fed into scintillation phosphors. Scintillation phosphors are just phosphors that glow, and so that it would glow, and that glow was picked up by a charge-coupled device and fed into digital reconstruction. And it still is, especially in bone densitometry now. So why we couldn't really use that in diagnostic was because the resolution wasn't there yet. Fan beams are very slow in addition to that, and since motion is the number one thing that degrades an image, it feeds back into the resolution. We had resolution problems on top of resolution problems. It could give us a wider possible dynamic range and possibly a higher sensitivity, at least at low exposures. meaning that we could adjust the density either up or down, really, which is a possible benefit, but again, the resolution just wasn't there yet. But if you look at figure 16-6 on page 299, you'll see what I mean by at low exposures you may have increased sensitivity. The response to digital imaging is linear response. We still use that H&D curve to represent contrast and density and our speed, image receptor speed. But realistically, the response rate of digital is linear. So where films and screens almost had a threshold exposure before you really started getting any kind of density, and that would be done in the toe portion of that curve that's represented in figure 16-6. The low exposures on CR and DR, even all the way back to where we were using scan projection radiography, could have been more sensitive. At the upper end of the exposure, what you see is film becomes more sensitive than the digital processing. So in CR, again, what we have is exposure to the plates. The PSP plate, the photostimulable phosphors are inside of the plate, and if you remember, in exposure they glow and they emit a little bit of light, but they don't glow as much as intensifying screens do. Instead of releasing all the energy that they absorb in the form of a glow, they're elevated to a metastable state so that they hang on to some of that energy. So the photostimulable phosphors have a storage capacity to them, so they hold on to some of that energy, and that's released inside of the reader during laser stimulation. So you get interrogation of the PSP plates, you get light detection with the sampling. Light is amplified, it's fed into a photomultiplier tube, and then it goes into analog to digital converter. With the A to D converter, the signal is digitized, manipulated, fed through the lookup table, and displayed on the monitor. In our DR types, again, we've got direct capture and we've got indirect capture. With indirect capture, what we have is conversion to light, and then it converts the light to an electric signal. So we've got two different types. We've got cesium iodide, and the cesium iodide is attached to a charge-coupled device, and then we've got cesium iodide that is attached to amorphous silicone. And each one of these kind of behaves at some level like a solar panel. And how a solar panel works is light hits the solar panel is energized to release electrons, and the electrons become your electricity. And instead of just being electricity in this case, what we're doing is we're quantizing how many electrons are captured, how many electrons are released and conducted, so that we can determine the signal strength, that signal being the X-rays incident on the image receptor. So we had cesium iodide to charge coupled device. We have cesium iodide to amorphous silicone, and the amorphous silicone requires a storage capacitor and a thin film transistor. And then we have direct capture, which is most like a solar panel. So the indirect capture of the cesium iodide to a CCD, that's a charge coupled device. The cesium iodide is a scintillation phosphor. That means it's photostimulable. So you make an exposure on it and it glows. And the reason we use the cesium iodide is because it has a high photoelectric capture. And that's just a fancy word of saying it's got a lot of electrons. So a lot of targets for the X-ray photon to hit, and since there's a lot of targets for it to hit, we get a lot of interaction on the plate itself. So it's relatively high atomic number. The atomic numbers for cesium and iodide are 55 and 53. And in that way, we get good light interaction and good light transmission to the charge-coupled device. So hopefully to just help you to remember what scintillation means. Scintillation, just the definitions of scintillation, are a bright flash or a spark, the emission of flashes or sparks of light, kind of like the twinkling of the stars. A charge-coupled device is a device that's used to manipulate and move electric charges so that you can manipulate them and digitize them so that you can use an analog signal and create a digital signal out of it. So what we have with a charge-coupled device is you have photoactive region. So what you've got is exposure on the cesium iodide. The exposure causes a glow. The glow is picked up by the CCD. It's got a photoactive region that picks up that glow. And based on the glow, it accumulates an electric charge. So the more glow that it receives, the more light it receives, the more of an electric charge it receives. Again, sort of like a solar panel. So the charge, the electric charge is proportional to the glow that it receives. So more exposure equals more glow equals better input for information manipulation. Now you got to think all the way back to our first semester physics with the semiconductors. It's a silicone-based semiconductor material. It has a P side and an N side. If you remember, the P side stood for positive, which means that it had too few electrons. And the N side was the negative side that had an overabundance of electrons. So the way a silicone-based semiconductor works is if you apply negative charges to the positive side, then what happens is those electron holes rush towards negative feed into the P side, so that basically what you get is a dead zone between the P side and the N side. If you remember, we call that the PN junction, positive negative junction. But if you put a electric flow to the inside, then what you have is the electrons that are already in the inside are repelled from the electrons that you supply to the inside, and you get a flow of electrons across the PN junction and all the way through the semiconductor. So you get no flow going if you apply electrons to the P side, but you get flow of electrons if you apply electrons to the inside. So it's light sensitive, and it has three characteristics, and that is sensitivity, dynamic range, and size. So see if I can make this play. I'm going to put you on pause for just a minute. Hopefully this will help you to understand how CCDs work.
Photographic technology has changed a lot.
Hopefully this will help you to understand how CCDs work.
Digital photography became cheap and convenient because of the CCD. Photographic technology has changed a lot in the last century. Digital photography became cheap and convenient because of the CCD, the charge-coupled device inside this camera. In the past, We just place a piece of film here behind the lens. But now we have a purely electronic imager to do all the work. Let me show you. Here it is, just a shiny slab, yet its details are fascinating. This CCD captures the image and then transfers it to the camera's memory system to record it as electronic data. When exposed to light, different sections of the CCD build up charge proportional to the light's intensity. We can then measure that charge and know precisely how bright that section of the image should be. If you enlarge a picture on your computer, you can easily see the tiny picture elements called pixels. Each one corresponds to a single section of the CCD. This is the essence of the digital camera. Several million of these sections of photosensitive silicon in a grid capturing an image. Now, the key to understanding how digital photography became cheap and ubiquitous lies in the ingenious way that the CCD transfers the image into the camera's memory. The easiest and most straightforward way would be to use wires to connect each pixel in an XY grid. But that presents a problem. Here's what goes wrong. After exposing the grid to light, we can use these wires to read the information pixel by pixel, measuring the charge on each section of the grid. This makes sense in principle, except all of the pixels and their electronic components leak a small bit of charge that distorts the charge coming from each pixel and leads to striations and patterns in the image. This distortion, called capacitive coupling, increases as the number of pixels increases. A CCD solves this problem in a very simple way. The pixels have no wires attached to them. A CCD is made from a slab of silicon. To make each pixel within the slab, engineers create insulating sections called channel stops. These divide the slab into rows. The surface is covered with a thin layer of insulating silicon dioxide, and then perpendicular to the channel stops, engineers deposit thin strips of metal, typically aluminum. Each pixel then is one section bounded by channel stops in aluminum. So now we have our grid of pixels. Recall that when light strikes the whole array, the silicon pixels build up charge proportional to the intensity of the light striking them. We then have a captured image stored as charge within each pixel. The great innovation of the CCD was how it moved the image from the silicon array to the camera's memory system without using external wires that would distort the image. The CCD shifts the charges from row to row without wires until they reach the bottom when a readout register transfers the charge to the camera's memory with very little distortion. The camera then counts the charges and constructs the image using that data. Now, one last important question. How do we get color? A CCD only detects total light intensity, which is useful for producing a black and white image. But for a color photograph, we need to separate the entering light into red, green, and blue. The most obvious solution is to filter the light into those three colors using three separate CCDs to capture red, blue, and green information and combine them into a full color image. However, engineers have created a cheaper solution. Instead of using three separate CCDs, they use a little math, so they only need one. In this consumer camera, they cover that single CCD with a filter with red, green, and blue pixel size sections. This creates an image coming out of the CCD that's a mosaic of these three colors. The camera applies an algorithm to estimate the correct colors for each pixel. For example, if a green filter covered a pixel, we would need to estimate the red and blue components of that pixel. To do this, they'd use the adjacent pixels and average the color intensity for the pixels in question. It works because the image's significant details are much larger than each pixel. This sounds implausible, but you've seen the results yourself. I'm Bill Hammack, the Engineer Guy. This video is based...
Sensitivity just refers to the speed of the image receptor system. So it's the sensitivity to the light or the stimulation. In this case, in indirect capture, it would be the sensitivity of the cesium iodide to intercept X-rays, and then it would be the sensitivity of the charge-coupled device or the amorphous selenium to convert the glow into something usable. In DR, it would just be the sensitivity of the amorphous selenium to exposure. Dynamic range refers to the ability to respond to a wide range of intensities. So we can get a large or a long shade of gray. The response in digital applications is linear rather than that S-shaped curve that we see in film. So again, if you look at page 299, figure 16-6, and compare the H&D curve for a 400 speed film screen system to the response on a digital imaging system, then what you see is that there's a 45-degree angle for the exposure on a digital system using a CCD, as opposed to there becomes almost a threshold exposure before you start to get into useful densities on screens and films. And what that means in screens and films is that you may have a lot of shades of gray and be able to record a lot of shades of gray, but they're so close to each other that you can't separate them out. You can't make any kind of visual distinction between the different types. So even though the film could record a ridiculous number of shades of gray, our eyes couldn't really detect it. So what we had with a film like this was that our film went from a very light exposure to a very dark exposure rather quickly. And what that did was it gave us very high contrast. And so if we had a structure where we had a wedge shape, like the foot or the T-spine, then what we had was a structure that we couldn't see both ends of the structure well. So if we were taking an x-ray on a foot, we had to know exactly where the patient's pain was. If they dropped something on their toe and we were shooting an entire foot, then we had to shoot with one mass value. But if they dropped whatever was heavy on their forefoot, maybe across the arch, then we had to use a totally different technique. And the two techniques would be specific to toes or foot. And if I shot with a toe technique, you couldn't really see the arch very well. And if I shot with an arch technique, you really couldn't, you'd burn out the toes. So with the DR and the CR and the computer algorithm processing our image and giving us that wider dynamic range, what we can see is the low density areas and the high density areas on the same image. So we have wider dynamic range. The literature says that film could record up to 10,000 shades of gray, but your eyes can't process that many shades of gray. You can't see that many shades of gray. So why demonstrate all those shades of gray whenever the difference between them are so minimal that your eyes can't distinguish them? So even though the digital processing might not have the same shades of gray, might not have as many shades of gray, it can take it and it can manipulate it and spread them out better so that you can see tissue types that you otherwise couldn't see with film. So the challenges we had primarily were bit depth, so that we can demonstrate the shades of gray that we needed to see, but also pixel size. So pixel size, individual detector sizes had to be small enough to have high spatial resolution. We had to have a large array of phosphors and CCDs. Small pixel size improves resolution. So you've all been around long enough to see kind of the evolution of resolution in televisions. So we have televisions now easily that are 72-inch, 80-inch televisions. So if you can think back to the earliest resolution that you can remember in a flat screen TV, and imagine that on a 72-inch or an 80-inch monitor, just how poor the resolution would be. It looks great on a small one, but if you use that same resolution matrix, same matrix size, then by the time you blew it up to an 80-inch TV, you'd have enormous pixels, and it'd be a TV that would be totally unwatchable. So we have to have small pixel sizes and small ability to detect through our CCDs individual stimulations. So the smaller CCDs, smaller pixel sizes help to provide that. So our next incarnation was cesium iodide with amorphous silicone. And it even became more like a solar panel. Your solar panel is basically silicone, and you make the sun shines on them and it liberates electrons. So in this case, what we've got is exposure to the cesium iodide. Cesium iodide glows and it picks up that light, and the light shines on the amorphous silicone, which provides um, the uh, the electrons for manipulation. If you look on page 300 and 301, you'll see figures 16-10, 16-11. I'll be referring to those, even 16-9, 16-10, 16-11. So what you've got in these individual signal detectors is an area that is capable of picking up the signal. And that would be your pixel detector. If you're looking at page 301, that would be your pixel detector. But you got the thin film transistor and storage capacitor, and those two are not sensitive to radiation. So the example that they're using here is that for each one of these pixels, only 80% is sensitive to the signal, to pick up the signal for manipulation, processing, and eventually signal display. They could have made those pixels smaller, but the percentage of the pixel that was taken up by the thin film transistor and storage capacitor would increase, which means that the pixel detector, the fill factor, what they call the fill factor, would increase the smaller the pixel size got. So there was a bit of a trade-off. They could have made them smaller and thereby increasing spatial resolution, but by increasing spatial resolution, the area that was sensitive to and capable of creating the signal would go down. So your fill factor will go from 80% down to 60% to 40%, depending on the size of your overall pixel. So patient dose would go through the roof. So we get better spatial resolution, lose pixel size or lose sensitivity. So they had to come to some sort of compromise between spatial resolution and patient dose. They could increase spatial resolution, but it would come at the cost of patient dose. Patient dose would go up. So finally, somebody else realized that we could make just the exposure on amorphous selenium. Truly becomes like a solar panel at this point. Make the exposure directly on the amorphous selenium. That's your direct DR. Gives you the highest spatial resolution for all the CR and DR applications. You still have a little bit of an issue with matrix size. The matrix size is still smaller and so inherently lower resolution than what screens and films are. But since the dynamic range is so much better, again, we've got a little bit of a trade-off there. And spatial resolution is really pretty good too. There are no scintillation phosphors. It's direct capture directly into the amorphous selenium. So what we have are three different elements. We've got capture element, coupling element, collection element with the amorphous selenium. That all happens at the same time, but with the indirect capture DR, then we've got each one of those working simultaneously, but each is its own step. So the capture element is what grabs the X-ray energy. The capture element in your indirect CR or indirect DR would be your cesium iodide. Your coupling element would be what bridges the gap between capture and collection would be what measures the energy and gets it ready for processing. So your capture element is your photostimulable phosphor. In your CR, in your DR, it's your cesium iodide. And we've been through that. It allowed for a wider area beam, shortened exposure time over scan projection radiography, and it could be gadolinium oxysulfide or amorphous selenium. The coupling element for the cesium iodide CCD is just a lens and a fiber optic assembly. For the cesium iodide amorphous selenium, you're directly attached one to the other. So thin film transistor, your amorphous selenium would be your coupling element. And for the direct capture, we've got amorphous selenium being both the capture and the coupling element. The direct exposure creates a charge through ionization, and the charge is stored in a capacitor until it's read. And just going all the way back to first semester physics, if you don't remember what a capacitor is kind of like a one-shot battery. We talked about capacitor discharge units where you plug the portable in and you build up a charge, and then you make your exposure, and the KVP would drop throughout the exposure. It's a capacitor discharge type unit. And a capacitor is just where you build that charge up. So you build a charge up, and then it stores that charge until you're ready to utilize the charge. So then we finally have the collection element. And then the indirect capture, what we have is with the cesium iodide CCD, is a photodiode. That's just a light sensitive device, and the charge coupled device. And the cesium iodide with the amorphous selenium thin film transistor is your collection element. I think in the previous slide I said it was the coupling element, but it's not. The capture capacitor is where the signal is stored and kept until it's ready for processing. Same thing with a direct capture, only we've got direct exposure onto amorphous selenium, and then the capture capacitor is charged and ready for manipulation, for image manipulation. So development of DR and mammography, we've had to use or couldn't use CR as a viable option, because if you can remember the development or the construction of the CR cassettes and the plates were that the phosphors lived at different depths within that plate. And because the light came off of those individual phosphors and they spread out because of divergence, then what happened was that we lost spatial resolution to the point that CR in mammography was not viable. When a cancer is detected or suspected, we do mammography. What they're looking for is what they call microcalcifications. And just like the term suggests, there are little bitty tiny pieces of calcium inside of the breast tissue. Now, breast tissue being inherently low contrast tissue, it makes it very difficult if any degree of ambiguity exists in the light signal that's coming off of those phosphors. So the spread of the light and the loss of intensity of the light because of the spread of the light, and also because of the loss of spatial resolution as the light spread out between phosphors, the spatial resolution just wasn't there for mammography with CR. So it wasn't until the DR phosphors got small enough that we could detect and visualize those microcalcifications that mammography could get away from films. So it wasn't until direct digital mammography came about with amorphous selenium with very high resolution, and the dynamic range was ideal for mammography. So the pixel sizes had to get small enough. The contrast was good, we could manipulate the image and draw out the contrast, so the spatial resolution was the issue. The contrast resolution and dynamic range wasn't a problem in mammography. When we're talking about resolution, we've got contrast resolution, we've got spatial resolution. And if the only thing that we refer to as resolution, then that's going to be your spatial resolution. Contrast resolution is always going to have contrast resolution, that quantifier contrast in front of it. So resolution, spatial resolution, that's your geometric factors. Those are your geometric factors. We're talking about sharpness for recorded detail. Spatial frequency. Spatial frequency is a relatively new term, and if you look in the glossary in Bouchon, it says the ability to image small objects that have high subject contrast. That's spatial resolution. Spatial frequency says measure of resolution, usually expressed in line pairs per millimeter. So really, spatial resolution and spatial frequency are pretty much the same thing. So spatial resolution is your measure of spatial resolution. It's measured in line pairs per millimeter, and it's the ability to see separate object as distinct. And the higher the spatial frequency, the better the resolution. I'm going to bring a couple of things over and show you. So spatial frequency is determined by geometric factors, focal spot size, matrix size. It's a system that demonstrates high spatial frequency is high resolution. So objects with high spatial frequency are harder to image. So spatial frequency applies not just to the image, but to the objects as well. So it means small objects that require high sharpness for recorded detail in order to visualize. And objects that are smaller than pixel size have very poor sharpness for recorded detail. So again, pixel size, matrix size plays into your sharpness for recorded detail. And if you have very small objects, they're very tough to see. So it's limited by the size of the pixel. If everything else is perfect but the pixel size is large, then resolution is just going to be bad. So when we're talking about measuring sharpness for recorded detail, we can use line pair per millimeter test tools. And for the computer itself, you've got in the QA or the quality control measures inside of your computer in your system, you've got built-in resolution test patterns. And it kind of looks like this. Once in a while, you may see your television go offline, and you'll get a resolution pattern that looks like that. This is what's supposed to be what we talked about in class, the STAR test pattern. These two are just line pair per millimeter test tools. So the resolving power of your computer is going to be determined, and also by your image receptor, and even by your X-ray tube, is going to be determined by where these things blur. So just on this size, I can see here, I can see the difference between those lines there, but below that, really to my eyes, they start to blur. You can't really differentiate them. So there's just different line pair per millimeter test tools. And traditionally, the STAR test pattern has been long considered to be the best for radiography. So modulation transfer function is kind of new to computer processing. It is spatial resolution and contrast resolution kind of blended. So we've got a definition here I'll bring up. We're going to look at a couple of different things. Modulation transfer function is spatial frequency response of an imaging system or a component. It is a contrast at a given spatial frequency relative to low frequencies. On the radiogram, objects having different sizes and opacity are displayed with different grayscale values. modulation transfer function is responsible for converting contrast values of different sized objects into contrast intensity levels on the image. So we'll take that and we'll take this into consideration as well. If I can get this into the screen. It doesn't want to cooperate. There we go. So the importance of modulation transfer function is that whenever we have low resolution, or not low resolution, but when we're trying to resolve small items, the contrast of that item becomes even more important. So I'll bring this back over. So again, we're looking at things that have very low line pairs per millimeter, so spatial resolution. And the contrast then becomes even more important, that we can separate those things out. If contrast resolution is poor on things with very low spatial resolution, where our line pair per millimeters blend together, then it compounds the problem. So the modulation transfer function, it's kind of a synthesis of both spatial resolution and contrast resolution to be able to make sure we can visualize the separation between these lines. So it's the ability to recognize and record objects as distinct and separate is what resolution is, but the modulation transfer function becomes, again, very important whenever we get down to those small areas. It's limited by pixel size. In CR, I think we might have mentioned that small image receptor detectors tend to be of the same matrix size and pixel size as large, or not pixel size, but matrix size. So again, back to what we were talking about in the analogy with televisions. If we have a small pixel size television, we put it on a small monitor, then we have the appearance of high resolution. But if we take that and we put it on an 80-inch monitor, our resolution decreases. So in some of our CR systems, that's exactly what they did. They used the exact same matrix size between small image receptors and large image receptors. So image receptor size in CR was sometimes determined by the resolution was determined by the image receptor size. So smallest image receptor size you could use was of the highest spatial resolution. So what we want are small image receptor detectors, we want small screen pixels, and we want a large matrix. What you use to control resolution, I apologize, this is way down at the bottom, is the focal spot size. Small focal spot size gives us the highest possible resolution. Contrast resolution is your dynamic range, and it's controlled by the bit depth. It is the number of shades of gray that can be recorded and demonstrated. So when we have high contrast, what that means is it's a very black and white image. There are very few shades from the lightest image to the darkest image on the image receptor, or on the TV screen, or on the computer screen. Low contrast is the opposite. You've got a lot of shades of gray. So going back to our H&D curve, again, we're looking at page 299, and we went through this in chapter 10, I think it was. What we see there with that 400 image receptor speed is a very vertical H&D curve, which means a high contrast curve. A horizontal H&D curve represents a low contrast curve. So comparing the response of the CCD in this case at a 45-degree angle, what we've got is inherently a lower contrast with CR and DR than what we had with film, which was a very high contrast. what we have in the image display after the computer algorithm is applied, that process is what we call automatic rescaling. So you make your exposure, and you've got the stored histogram, which is your lookup table inside of the computer. Your computer seeks to make your image look like the stored histogram in as much as the contrast and density goes. So that process is automatic rescaling. And then you get your image. And that image is not the raw data, but the image that has been post-processed, or the image that has been processed against the computer algorithm, is what needs to be sent to the radiologist. Sometimes you have a tendency to want to manipulate your image, adjust the contrast, adjust the density, see if you can make something stand out a little bit more. And that's fine if you do. Just make sure that you save the original, and don't overwrite the original with new post-processing. Post-processing is your window and leveling. So don't you want to save the original and send that to the radiologist. If you happen to save a second one and send both of them to the radiologist, that's fine, but never send just the post-processed image to the radiologist. Always send the original. If you send them both, that's okay. So window level increases or decreases brightness, as opposed to width increases or decreases contrast. So signal to noise ratio is the amount of good signal that we have versus the amount of bad signal that we have. So a 1-to-1 ratio means that the good signal and bad signal equal. What we want in signal to noise ratio, signal to noise, we want the higher signal and lower noise ratio. So a lot of different types of noise that we can have. We've got electronic noise, we've got scatter radiation, and we've got quantum model. So the old saying about computers, garbage in equals garbage out, applies here. The better signal that we have with the least amount of noise, the better image we can display. So we want to limit the scatter radiation. We want to eliminate quantum model if at all possible, and not have electronic noise on the image. We've walked through this, patient dose and image receptor response. If you remember, CR was equivalent to a 200 speed screens and film combination. So whenever we made the change to CR, our dose naturally went up because we had to reintroduce those photons that are the amount of signal to the image receptor. So we had to increase our technique. And since we had our contrast was less dependent on KVP and more so on the computer algorithm, we could increase KVP and increase the patient dose less than if we were to increase the mass. In other words, if we would have increased the mass by a factor of 2, because it was equivalent to a 200 speed system, and we're using 400 speed systems, then the patient dose would go up by 2. By increasing KVP by 15%, the patient dose goes up, but not as much as if we double the mass, because we get more penetration through the patient. So it's slower, inherently higher dose, and the accurate technique is just as essential in CR and DR as what it was in screens and films. The problem that we ran into once we got to CR is that because we could post-process some of the density off of the image, or the density may not even show up on the image, and the only indication that you had that you had overexposure to the patient was the S number, people started shooting naturally with higher doses, because you could, if you shot too low of a dose to the patient, then again, you're at a position of garbage in equals garbage out. You don't feed the receptor quite enough radiation, and you get a bad image. You feed it just a little bit too much, and you're okay. So what we had was a situation where people started getting lazy, and instead of knowing what their technique should have been, the technique wasn't as essential for image production, but it became more essential for patient dose. What I mean by that is people started shooting with too high of a dose intentionally so that they wouldn't accidentally shoot with too little dose, and it led to what we term dose creep. And dose creep is a problem. It's a problem, it's an ethical, it's a moral problem, and it's just a laziness problem that hopefully, we've kind of addressed somewhat. So learn your techniques, make sure that you don't overexpose the patient. Detective quantum efficiency is kind of a big term for the likelihood that the photons will interact with the image receptor. So going back to our phosphor types, what we want is a phosphor that has a lot of electrons. So a lot of electrons means a lot of ionization, regardless of what kind of technology we're using, be it CR or DR, the more signal we have. So DQE is closely related with atomic number. And with a higher DQE, having a lot of electrons to liberate, generally we're going to require a lower dose to make the same exposure as with a phosphor that has a low DQE, or an image receptor that has a low DQE. So going back up to our indirect capture, if we used anything besides cesium iodide, if we had something with a lower atomic number, I don't know, say 40 and 43, then what we would have is, for the same exposure capture, we'd have to have a higher dose to the patient. So DQE, we want to use the phosphors with the highest possible DQE and still accomplish what it is that we want to accomplish. If atomic number got too big, then our binding energies may cause our electrons to be bound tighter than our average X-ray beam energy. So we want adequately high DQE, but we don't want the DQE or the atomic number to be so high that those electrons won't be ejected whenever they're interacted on by photons. So optimizing patient dose. Whenever you're phototiming, positioning is absolutely essential. Whenever you're setting techniques, make sure that you don't fall into the dose creep trap. The technique creep, make sure that you learn your techniques and you don't overexpose the patient, because it truly is a moral, an ethical, and a professional obligation that you learn your techniques and you don't overexpose the patient. Learn what your index numbers should be. They're only accurate if everything else is right, if your collimation is right, if your centering is right. So again, make sure that your positioning is as spot on as you can get it. And then again, utilize higher KVP techniques whenever you can. KVP doesn't affect your contrast nearly as much as what it used to on screens and films, so you can naturally use a little bit higher of KVP. That's not to say that you want to use maximum KVP with every single patient, but there's a little bit more flexibility in usage of higher KVP. And I think that in your career, we're going to see KVP values increase with mass values decreasing. Of course, that comes at the risk of quantum model, but it should further save patient dose.